Okay, this is problem 2 for EE140 Spring 2019 Midterm 1B, and the question is, a dielectric sphere radius A, epsilon r equals 2, is carrying a volume charge density of rho equals 3r. It is completely enclosed by a spherical shell of outer radius B, epsilon r equals 4, and has a uniform charge density equal to -5 coulombs over meters cubed. Find E of r in all regions. And so, as you can see, I've already worked this problem out. And I'll be going through it step by step. So the first thing to note is that it is a dielectric sphere, and so we can use Gauss's law because the E field is perpendicular to the change in area on all points of the sphere. So this is why we can use Gauss's law. And as Dr. Kwok states in his textbook, the displacement vector D is used to separate the contribution from free charges and polarized charges. The enclosed integral d dot dA equals Q inside, and D is just E naught ER E times A equals Q inside. And D is given by epsilon naught, which is the permittivity vacuum, times epsilon r, which is the relative dielectric constant of the medium, and times the E field. And epsilon r is used to indicate how easily the dielectric material can be polarized by nearby charges. And the question asks us to find E of r in all regions. So there's a region where r is less than A, r is between A and B, and then a region where r is greater than b, which I will show you how to do once I finish these two and I have more room. So from the problem statement, we know that ER1 is equal to 2. So ER1 is equal to inside when the sphere is r is less than A, and ER2 is equal to 4 when r is less than B but greater than A. And so let's do the first one where the radius of the Gauss surface is less than A. It's going to look like this, radius r. So this is a Gauss sphere. So a Gauss sphere of radius r less than A. And we just take this equation over here and start plugging in. So we have E naught. E of r, in this case, is just 2. It says right here, it's 2. And then E is what we're solving for. So E times, and then it's going to be the surface area of the Gauss surface, so that's pi r squared. And that's going to equal to Q inside. How do we find Q inside? Q inside is just the integral of rho dV. Since rho is a function of the radius, and the radius is changing, we have to take the integral. That's why we take the integral of rho dV. And here dV is just the surface area times the change in radius. So it is surface area times dr. And so that's what I'm doing here. Rho, as was stated earlier, is 3r. So 3r times, and dv is 4 pi r squared dr. And we're going to take that integral from 0 to r because that's how big our Gauss surface is. And so if we simplify this, this becomes E times 8 pi r squared epsilon naught. And that's, if we solve this integral from 0 to r, we end up getting 3 pi r to the 4th. And then simplifying this, so taking this and dividing by that, the pi's are going to cancel out, and it's going to turn into 3r squared over 8 epsilon naught in the r hat direction. E is in the r hat direction, and the r hat direction is along radius r. So E is pointing outwards in all directions, since it's a sphere. Now the second part is when R is between, we want to find the E field when R is between A and B. So it's greater than A but less than B. And we're going to make a second Gauss surface. So this is our new R. It's greater, the Gauss surface is greater than A but less than B. And so again, we're going to use this equation up here where we have epsilon naught, that's not changing, but notice how now instead of 2 we have 4, and that's because this new Gauss surface, when it's between A and B, epsilon R changes to 4. We're no longer inside A anymore. We're between A and B. So we're going to use 4 because that's the dielectric constant. So 4 times E, again we're solving for E, and then again the surface area of our Gauss surface is still 4 pi r squared, where r is again the distance from the center of the sphere to where we made our Gauss sphere. And then Qn, so this is where it gets a little complicated. So Qn is just the charge enclosed in the Gauss sphere. So we know what the charge enclosed from 0 to A is. So from 0 to R, we know the charge enclosed is this. And if we were just to change this integral from 0 to A, then this would just become 3 pi A to the 4. And that's what we have over here. So that's the charge enclosed in this whole sphere. But now what's the charge enclosed from A to your Gauss surface, right? From A to R. Well, that's given by this integral, which is, again, looking over here, it's just rho dV. So we have the charge density is stated that between the sphere enclosed by B is -5 coulombs a meter cubed. So rho dV. Our rho is just -5 as stated in the problem, and then again dV is just 4 pi r squared dr, and the bounds are A to R because we're trying to solve the charge inside from A to the Gauss surface, which is a distance r from the center. And so if we just simplify this right here, the left hand side of the equation, it becomes E times 16 pi r squared epsilon naught, and then rewrite this, it's 3 pi A to the 4, and if we solve this integral from A to R, it's going to give us -20 pi r cubed over 3 minus A cubed over 3. Okay, so again, this is the charge enclosed, the total charge enclosed from the center to this Gauss surface over here, the second Gauss surface, which is between A and B. And if we simplify this, we're going to take the right hand side of our equation and we're going to divide by the left hand side, the 16 pi r squared epsilon naught. And this will simplify to the E field when we're between A and B is going to give us 3A4 over 16 r squared epsilon naught minus 5 over 4 epsilon r squared times r cubed minus 3 minus A cubed over 3 in the r hat direction. And now let's move on to when r is greater than b. Okay, I just rewrote r is less than a over here, the E field. So now let's do when r is greater than b. So we're going to follow this equation again, E naught. Our dielectric constant it's outside of the sphere is in air. It's not given, so we just assume that it's going to be in air. So we're going to assume 1. E of r air equals 1 times E. Again, that's what we're solving for, the electric field. And then this time, the Gauss surface is greater than B. So the Gauss surface is from the center to this, or the radius is from the center to the Gauss surface, which is greater than B. Again, the surface area is 4 pi r squared. And I'm running out of room, so I'm going to write this over here. This is equal to, well, like how we did with when r was between A and B, we're going to look at this here. This was Qn, but remember this is in terms of r. So we don't want this in terms of r because we know that r is greater than B. So the total charge enclosed when r is greater than B, it's going to be the charge inside the first shell, right? And the shell is has a radius a, so that's 3 pi a to the 4. And then this right here was for when our Gauss surface was between A and B. But our Gauss surface is now greater than B, so we can go ahead and substitute B into the place of R. So minus 20 pi B cubed over 3 minus A cubed over 3. And if you don't believe me, then you can do the integral if you'd like. And the integral is, remember, just rho dv, and it would be from, so it would be 3 pi a to the 4 plus negative 5, which is rho, remember, and dv is 4 pi r squared dr, and you're trying to find the charge from A to B, and it'll just give you this. So you have the charge inside of A and the charge inside between A and B. So that's the total charge when R is greater than B. Okay, so this is your right-hand side of the equation, this is your left-hand side. We can go ahead and simplify this. This becomes E 4 pi r squared epsilon naught is equal to 3 pi a 4 minus 20 pi b 3 over 3 minus a 3 over 3. Okay, and then we can just go ahead and simplify by taking this divided by this. So it's going to be 3a to the 4 over, pi's are going to cancel out, so 4 r squared minus 5. Pi's are going to cancel out, so 5, oops, this is epsilon naught, so it's going to be 5 over r squared epsilon naught times b cubed over 3 minus a cubed over 3. And the r hat direction. And that is your answer when r is greater than b.